Today's lesson is on centripetal force, and the specification points we're going to be covering are 106 for the home A level, understanding that a resultant force is required to produce and maintain circular motion, and if you're doing IAL, that is specification point 90. To do this, we have to appreciate Newton's first law properly. And so Newton's first law officially states an object will continue in a straight line at a constant speed unless a resultant force acts upon it. So we've got a straight line and constant speed here. Unless a resultant force acts upon it. So what that says is that if you get a resultant force, which remember is the remainder of two forces acting along the same line but in opposite directions, if you get a resultant force, then it will either stop the object moving in a straight line or change its speed. We can summarize Newton's first law by saying that resultant forces cause acceleration. That's the simplest way of thinking about it. So if you have a resultant force, you know that the object is going to accelerate. In other words, it is either going to speed up, slow down, or change its direction. The flip side of that is, if you witness an object accelerating, then you know that there must be a resultant force in the direction of that acceleration. And that realization becomes very important as we work through A-level physics. See an acceleration, must be a resultant force. Which leads us on nicely to this idea of how could an object be moving at a constant speed and yet be accelerating. So this catches out people who think acceleration is just a change in speed. So if an object is moving in a circle, so if we look at these people on the roundabout here, they're moving around in that direction, you know that if you cut the chain here, that person would shoot off at a tangent to the circle. So because they are moving around in a circle, their direction is continuously changing, so we know that they're accelerating. Remember, resultant forces cause acceleration. If they're accelerating, there has to be a resultant force. And the direction of their acceleration is towards the center of that circle, which means that the resultant force has got to be towards the center of that circle as well. And this is the thing about resultant forces. The resultant force that keeps an object moving in a circle, we call it the centripetal force. But you must appreciate that the centripetal force is not a named force like electrostatic force or gravitational force. Centripetal force is the remainder of when you take away the two forces that act along the same line and in opposite directions, whatever is left over. And it's interesting to look at what forces might be supplying the centripetal force in any situation. In this situation, for example, so this is a satellite that is orbiting the Earth. The first thing you do if you want to identify what's causing the centripetal force is you have to look at the circle that the object is moving in. So very roughly drawn, this is the circle that the satellite will be moving in. And identify where the center of that circle is. Obviously, that's going to be the center of the Earth. What you need then is you need a force that is acting towards the center of the Earth. And obviously in this case, that's going to be gravitational force. And this is the easiest situation. Any object orbiting the Earth, the centripetal force is caused by the object's weight. Here's another situation, objects moving around in a circle. Let's again use our method. Let's look at the circle that they're moving in. That's the circle they move in, and there's the center of it in there. So we need a force that's going to be acting towards that center. And we know that then that force will be providing the centripetal force when we take away any forces in the opposite direction. And the only force that's acting towards the center of that circle in this situation is the friction between the tires of the cars and trucks and the ground. So it's the friction that is supplying the centripetal force. Things get a little bit more complicated in this situation. We can't see the circle here, but we can imagine it. It's in that direction. I've drawn it as a smaller circle than it would be, but the center is somewhere in this direction. So we need, let's take from a bike, we need a force that's going to act towards that center of the circle. Now you might think to yourself, well, this is the same situation as the roundabout, and it is at lower speeds. So there is friction between the tires of the bike and the sand that they're traveling on, and that friction is going to supply some of the force towards the center of the circle. But as the bikes speed up, and we'll talk about the equation for centripetal force in a bit, as the bikes speed up, the problem that you have is that that friction isn't going to be enough to keep them in that circle. And so what the motorcyclists do is they lean slightly. So if you take this contact point between the tire and the ground, the normal contact force, remember, balances the weight of the motorcycle plus the cyclist. And in a normal situation, if the bike was sitting vertically straight upwards, that normal contact force would be vertically upwards. But when you tilt the bike in this manner, what happens is the normal contact force points in that direction there. And because it does that, it has a vertical component that is continuing to balance the weight, and it has a horizontal component. And so that horizontal component of the normal contact force then helps friction with keeping the object in moving in a circle. Now, of course, the faster they go, the more centripetal force they're going to need, and again, we'll look at that equation in a moment, which means that the more the motorcyclist has to lean over to the side so that you get this normal contact force providing more and more horizontal component. It will increase in general, but more horizontal components so that it can provide more centripetal force. Airplanes are a very interesting situation. So if you take an airplane, and when it's flying level like this, the lift from the wings balances the weight of the airplane. And that's the idea, the reason it doesn't accelerate upwards or downwards. Now we're talking about as it's flying at a particular height and at a constant speed. On Earth, if you want to turn, you have to push against something to turn you. So you need a resultant force in order to turn around. Unfortunately, the airplane doesn't have that possibility. So what the airplane does, the pilot does, is that they tilt the wings of the airplane. And again, remember, your weight is always going to be acting downwards. That's the weight. The lift force is perpendicular to the wings. So now our lift force is acting in that direction. And again, you'll have horizontal and vertical components of this. So the vertical component continues to balance the weight. The horizontal component is towards the center of the circle that the plane is going to be flying in, and this is providing the centripetal force. There is a problem with this, though, if you think about it. There's only the lift force is generated from the wings and caused by the speed of the airplane. So you really have, depending on your flying speed, you really only have a fixed amount of lift force. So when you turn like this, what happens is, of course, that some of the lift force is being used to put you in a circle and not being used to balance the weight. And the aircraft will start to descend. You could, of course, fix that by flying faster, and therefore increasing the lift force. But by doing that, by flying faster, you also need more centripetal force, and that's going to cause you problems. Okay, so how do we calculate the size of this centripetal force? Well, if we remember back to Newton's second law, which is basically the mathematical description of Newton's first law. Newton's first law tells you, again, that resultant forces cause acceleration. Newton's second law tells you how much acceleration you get for a given resultant force. And remember, very importantly, and of course, classically we write Newton's second law as that, this F here, that's resultant force because it's causing an acceleration. So it isn't the total amount of any particular force, it is whatever the remainder force is. In the previous video, we had a few expressions. We're going to focus on two of those for centripetal acceleration. And if you haven't seen that video, it's deriving the equations for centripetal acceleration. I would recommend you go back and have a look. So what we had was A being equal to r omega squared, and A being equal to v squared over r. And it's a very simple substitution. We're simply going to put those in there and say that means that F is equal to m r omega squared, or F is equal to mv squared over r. Now, if we look at this, you can see if you increase the speed, and speed is the biggest factor here in terms of how much centripetal force. If we increase the speed, it causes an increase of the centripetal force of a square. radius and mass of the object do obviously increase as the radius of the circle increases, because you're increasing the bottom of this equation here, then the amount of centripetal force is going to decrease, so the larger the radius of the circle, the easier it is to keep the object in there. This one we use for, I'm going to call it normal things like cars and planes, where we can measure their speed very easily. Radius is easy to measure, they're human-sized object. This one becomes very useful when you start looking at orbits of planets. And when we do our gravitational section, we use this a lot because we can find out the time period of the orbit by using omega squared here, or use the time period of the orbit to find the gravitational force. Okay, so let's have a look at some different kinds of circles, because obviously there are different ways in which you can move in a circle, and our first one is this one. So this is like a conical circle, so you have an object that is suspended from a point up here at the top, and then it's going to swing round in a circle around the bottom here. Let's look at the forces that are acting on it. As we know, the weight, which is calculated by mg of the little happy face here, is going to be acting straight downwards. The tension, as the object moves in the circle, is provided by this string. And of course, that tension has a vertical and a horizontal component. And that's the key part here. So the vertical component of the tension is going to be equal to mg, because the happy face is neither accelerating upwards or downwards, so the two vertical forces have to be the same size and have to be balanced. It's moving around in the circle, and the center of the circle is there, and therefore whatever force is pointing towards the center of the circle, that is the one that is going to be providing the centripetal force. And of course, in this case, that is the horizontal component of the tension of the string. And if you know the angle at which the happy face is circling, you can calculate how much the horizontal component of the tension of the string would be. So if we label the centripetal force here as Cf, then we can say that's the horizontal component, that the cos of theta is going to be the horizontal component, adjacent over the hypotenuse, which will be equal to t, and therefore our centripetal force will be t cos theta. Now, if you don't happen to know what t is, then you can always use the idea that the vertical component of t would be equal to mg. And if you know the mass of the happy face, you can then calculate what the vertical component of that tension would be. If you speed up your turning of the happy face, it's going to swing out further. And this is an important point. Remember that the centripetal force that's required is mv squared over r. So if you increase the phi of the happy face, then you need more of that centripetal force, which means you've got to increase the size of that horizontal component. And in order to do that, you've got to make sure that it is traveling in a more horizontal circle. So the happy face would swing out this way. Of course, the vertical component still has to balance mg. So the total tension in the string is going to increase overall. This diagram is meant to represent something moving in a vertical circle. And so I've just taken a standard picture and put it in 3 different places. And let's think about, we know that the center of the circle that this object is moving in, it's a person sitting in a chair. Let's think about the forces that are acting on the person. And we're going to start this at the top. So at the top, obviously, mg is the force acting. And it is acting towards the center of the circle. Because this person is sitting in a chair and is upside down at this point, there's a normal contact force with the chair and the person's bum. Because that's acting towards the center of the circle too, that can contribute to the centripetal force. We know what centripetal force is calculated by mv squared over r. So mv squared over r is going to be equal to the weight of the person, mg, because that's the force that's acting towards the center, so that must be the force that is keeping the object moving in a circle, plus your normal contact force. Interestingly enough here, there may be no normal contact force, depending on the speed the person is going at. And this is how fairground rides in which you go upside down. This is how they work. So this speed is very carefully calculated. The speed must be enough so that it is at least equal, mv squared over r is at least equal to mg. That means you are not going to fall out of your chair. You can think of it as your mg is too busy providing the centripetal force to cause acceleration towards the center of, towards the Earth, and therefore there is no mg left over to cause acceleration towards the Earth, and you don't fall. If you go greater than that exact speed where they're equal, then the normal contact force kicks in. And what you will feel is that the seat is actually pressing you downwards. And what that is doing is actually ensuring that you stay in the chair. So it would be risky to be running one of these fairground rides where mv squared over r is exactly equal to mg. You're better off going faster so that the normal contact force becomes part of the equation and it keeps you in the circle and not falling. If we go to this middle part, the middle part is the most straightforward part. mg is obviously acting downwards. The normal contact force, she should be faced in the opposite direction. The normal contact force is acting towards the center of the circle. The chair should be on the other side so that she's being pushed to the center. I couldn't manipulate the picture to do that. And therefore, the normal contact force is equal to mv squared over r. Fairly straightforward. And by this, when I write this, I mean the normal contact force is providing the centripetal force. So if you want to find out how much the centripetal force is, you could either have some way of finding the normal contact force, or you could find the normal contact force by figuring out how much the centripetal force was. Down at the bottom, so let's label our forces again. This time, mg is acting in the opposite direction to the center of the circle. And the force that's acting towards the center here is the normal contact force. That means that the normal contact force must be the force that's providing the centripetal force. However, as we know, the normal contact force has its day job. It also has to balance the weight of the person, because if it doesn't, then she's going to accelerate towards the center of the Earth. So in this situation, the normal contact force is going to be equal to mg, so it's doing its day job, plus it's keeping the object moving in a circle. And that means that at this point, at the bottom of the circle, the normal contact force is at a max, because it has to do both jobs at the same time. Whereas at the top of the circle, it might drop to 0. If you balance the speed exactly so that the centripetal force required is equal to the weight. Now, these are important equations to be able to play with, and I will be doing some questions in the next video showing you how to work with these equations and how to figure out how much centripetal force there is, how much normal contact force is required, etc., etc. There are all kinds of situations in which objects move in a circle, and there's no way of covering all of them, but there are some basic principles that we can look at. So suppose there's a car and it's up on the top of this bridge, and it's a humpback bridge, so it's got a center of a circle which is right there. And as the car goes over the bridge, something must be providing the centripetal force. And of course, logically, we know that that must be mg because that is the force that is acting towards the center of the circle. But remember that mg is a fixed amount of force, your weight. It depends on the mass of the car and the Earth's gravitational field. The Earth's gravitational field isn't going to change all that much, and the mass of the car is relatively fixed as it goes over the bridge. So mg is a fixed amount. And we know that if the car is going to stay in this circle, in other words, it's going to travel over the bridge, then it must be less than mg, or at best, it must be less than or equal to mg. If the mv squared over r gets bigger, so if you increase the speed at which you go over this bridge, this side of the equation, mv squared over r, is going to get greater, but it will exceed the amount of mg. And that means that you no longer have a resultant force keeping you in the circle. And so what the car is going to do is it's going to take off, even slightly. So as you drive over a humpback bridge like this, you can lift the wheels off the ground and land down. I wouldn't recommend doing that. This is the reason why bridges like this tend to have quite low speed limits on it. Of course, if mv squared over r is less than mg, then you get a normal contact force. So you've got mv squared over r plus our normal contact force would be equal to mg, because remember, mg is the force. The resultant of that with the normal contact force is going to be providing the centripetal force. What about the opposite situation, where instead of being a humpback bridge, it's like a bowl that you drive down into? Again, all you have to do is figure out what your forces are along that line towards the center of the circle. So we've got mg and the normal contact force. And I haven't drawn these arrows to scale or anything like that, so mg does not have a role in providing the centripetal force here. The normal contact force does. So normal contact force is going to be the force that's providing the centripetal force, or mv squared over r. Remember that the normal contact force also has another job. It's got to balance the weight of the car, otherwise the car would accelerate into the ground. And that clearly does not happen. So just like the lady who is moving around in the circle, at this point the normal contact force has got two jobs. It's got to balance the weight of the car, just like it does all the time. Then it's also got to provide the centripetal force. So if you drove into a dip like this, you would feel the chair of your car pushing on you, because that push that you feel from a chair is the normal contact force. And that has got to increase to keep you in the circle so you feel the chair pushing. And what about this scenario? So this is like the girl in the chair. When you go do a loop-the-loop in a ride like this, and you are upside down but don't fall out. The idea here is to keep mg, keep the weight busy, providing the centripetal force, so there's none left over to cause acceleration towards the ground. And so there's the center of our circle. We identify the forces that are acting towards the center of that circle, and that would be mg and our normal contact force. And so we know that if the normal contact force is 0, then mg is providing all the centripetal force. Now you have to be very careful designing this right, because of course you can't have mv squared over r being less than mg. Absolute minimum v here, or the combination between mv and r, an absolute minimum here has got to be so that mv squared over r is equal to mg. And this is the problem with these rides, is that of course you don't know necessarily, and obviously those m's are going to cancel, you don't know necessarily the masses, but it's v squared r and g that count here. So what they do is they say, all right, well, we're not going to take any chances with this. We'll increase v until mv squared over r is greater than mg, and get the normal contact force to then kick in. It presses the people downwards, but actually it's pressing them downwards to keep them in the circle and not to accelerate them towards the center of the earth. If it wasn't there, you'd have to have that very fine balance of between v, r, and g. Okay, so let's go back and look at our specification points that we had at the start. Understand that a resultant force is required to produce and maintain circular motion. We know what a resultant force is. It is a remainder force. In order to get an object to move in a circle, we have to have a resultant force. We've got to identify what force is moving towards the center of the circle. That will be the one that is providing the centripetal force. And to maintain. If at any point that force isn't provided anymore, if the chain on the roundabout breaks, then the object will no longer stay in the circle and will move off at a tangent. The next specification point is using the equations for centripetal force. And so that's what I'm going to do in the next video. Make sure you check it out. I'm going to do relatively complex ones. My Patreon page, I'll be doing more exam questions, even more complicated ones, and talking you through how you should be thinking about these problems. So again, if you sign up to be a patron, then you'll be able to access those.